There are two active groups in the compound given in question number 25. They are an aldehyde group and an ester. The Grignard reagent works on the aldehyde, ketones, and carboxylic acid chlorides and ester groups to produce alcohols. This is through a nucleophilic addition reaction of the Grignard reagent with the carbonyl carbons involved. With aldehyde groups, it will produce a secondary alcohol, while with ketones, it produces a tertiary alcohol. But in formaldehyde, it will produce a primary alcohol. Reaction of the Grignard reagent with esters occurs in two steps, finally to produce tertiary alcohols. In the first step, there is a nucleophilic substitution, and in the second step, the usual nucleophilic addition to a carbonyl carbon occurs. In the compound given, there is the carbonyl carbon of the aldehyde to which CH3 would be added, and then an alcohol would be produced once it is hydrolyzed. And there is an ester for which initially there would be a nucleophilic substitution with OC2H5 removed and CH3 replacing that end. And then there will be a nucleophilic addition to the carbonyl carbon produced. And C2H5OH will also be produced once it is hydrolyzed. But it is not the major component. As question number 26 is concerning a reductant reaction, we can recall the reductants used in organic chemistry, which are lithium aluminium hydride, sodium borohydride, hydrogen nickel, and sodium ethanol. Of the above reductants, lithium aluminium hydride is capable of reducing carboxylic acids, aldehydes, ketones, amides, and esters as shown in the diagram, but they are not capable of reducing double bonds. Sodium borohydride also has the capacity to reduce aldehydes and ketones, but they don't have the capacity to reduce carboxylic acids or amides. Hydrogen or nickel, on the other hand, has the capacity to both reduce carbonyl carbons into alcohols and also to reduce double bonds. Therefore, in the reaction, the ketone component is reduced to an alcohol, while the amide component is reduced into an amine. Reaction of a ketone and an amine produces an imine through a two-step reaction. Therefore, the final end product would be the one shown here. The first statement of question number 27 is false because ammonia, although most of the time is a considered base, can also have acidity in reaction with sodium and other metals, and it forms NaNH2 here. Reaction of ammonia with oxygen can occur under two conditions, catalytic and non-catalytic. In the catalytic condition, it produces NO gas, while in the non-catalytic condition, it produces N2 gas. With Nessler's reagent, ammonia gives this brown precipitate, which is part of the identification reactions of ammonia. Typically, ammonia reacts with metals to form the metallic amides. With magnesium, copper, and lithium, it also forms the metallic nitrides. The effect of electronegativity on the structure of a compound is considered in the fifth statement. NF3 and NH3 both have the structure of a tetrahedron, except one corner is occupied by the electron pair. This will cause the bonds to be repelled away from that point, which reduces the angle from 109 to lower values. But in NF3, the higher electronegativity of fluorine causes the electron cloud to be attracted towards fluorine, and therefore the repulsion between the bonds is less in NF3 compared to NH3. Therefore, NH3 has a higher angle because of the repulsion between the bonds, while NF3 has a lower angle because the repulsion between the bonds is less because the electron cloud is widely dispersed. In question number 28, an electrochemical cell similar to the voltaic cell is given, except that here there is a tin electrode instead of the usual copper electrode. If you understand how the voltaic cell functions, then you'll be able to understand this question. In the voltaic cell, we connect two different electrodes through conducting material like a salt bridge and a wire. When you connect two electrodes like this, when one of the electrode is more reactive than the other, then that electrode will subject itself to oxidation, and therefore that electrode is the anode, and the other electrode will take up the electrons that are released by the first electrode, and it will become the cathode because it takes up the electrons and is subject to reduction. So, therefore, zinc is the anode where oxidation occurs and electrons are released, which flow from zinc to tin. Alkyl chlorides and amines react to form amides. Aniline reacts with alkyl chlorides in a similar manner, supported by the fact that aniline is an activating agent of the benzene ring. For this second statement, aniline being a base doesn't react with a strong base such as sodium hydroxide. Aniline reacting with bromine water forms tribromoaniline, which is a white precipitate. The reaction of aniline with nitrous acid prepared in the form of NO2 and H2SO4 occurs under two conditions to produce different results. First is at a temperature 0 to 5 degrees Celsius, and the second is at a higher temperature. In the first case, diazonium salt is produced. In the second case, phenol is produced. The ability of aniline and amines to act as bases depend on their capacity to donate their lone electron pair to an acid. But in aniline, the lone electron pair is donated into the benzene ring to strengthen the resonance, and therefore the ability to act as a base is reduced. In question number 30, we have to consider the equilibrium reaction of dissolution of the compound given. Any addition to the product side of this equilibrium reaction will drive the reaction towards the reactant side, that is, reduce the solubility. Similarly, any reduction in the product side of the reaction will drive the reaction further towards the product side, that is, increase the solubility. Therefore, addition of the conjugate base of acetic acid will reduce the solubility. Addition of dilute HNO3 into the solution will remove the conjugate of acetic acid by forming acetic acid, and therefore will increase the solubility. Addition of ammonium hydroxide will remove the Ag plus ion from the solution by forming silver hydroxide, which then will precipitate as silver oxide. Therefore, this will increase the solubility. Addition of AgNO3 will directly increase the concentration of Ag plus and therefore drive the equilibrium backwards, therefore reducing solubility. In question number 31, there is a reaction given along with its enthalpy value, which is negative, which means energy is released during the reaction. This energy is used to heat up the system. This question is based on Le Chatelier's principle, which states that there is an external stress in a system, the system will adjust in such a way that the stress is partially offset and the system reaches a new equilibrium position. By stress, what is meant in Le-Chatelier's principle is changes in concentration, pressure, volume, and temperature. If you consider this reaction, on the product side, you have 1 mole of solid and 1 mole of gas, while on the reactant side, you have 2 moles of gas. And on the product side, there is an increase in temperature. When there are more number of moles of gases, then the pressure on that side is higher. Therefore, if there is an increase of pressure, then the reaction would proceed towards the right. While if there is an increase in temperature, the reaction would proceed towards the left, and vice versa. As there is a single pi bond in each of the carbon atoms, all of them must be sp2 hybridized, and therefore the single bonds must be at 120 angle between one another, and they must all lie in the same plane. They cannot be in a straight line because of the set angle. Solvay process is used in the production of sodium carbonate, which is mainly used in the production of glass. The first stage in the Solvay process is to purify saturated brine, the sodium chloride, and then react it with gaseous ammonia. The ammoniated brine is then carbonated with carbon dioxide, which finally forms sodium bicarbonate. This is insoluble in the brine solution because of the common ion effect, and so it can be filtered. And once you heat it, it decomposes to anhydrous sodium carbonate. Next, carbon dioxide is stripped by heating the solution, and then CO2 is reused again to carbonate the initial brine solution. Then NH3 is also driven off by using alkali, here a slurry of lime in water, calcium oxide, calcium hydroxide can be used. Then lime is obtained by heating limestone, which also will give CO2, which again can be used in the initial steps. So based on this knowledge, the reactions A and B are correct. Question number 34 is based on the rate of reaction of an elementary reaction. In any reaction, the rate depends on a number of factors: temperature, physical state of reactants, pressure, concentration, catalyst, and the presence of radiation. These are expressed in the rate law, where concentration is directly mentioned, but the constant K is influenced by the other factors. The statement B is based on a practice that is used to increase the yield, that is, removing the products from the reaction medium. At equilibrium, notice that the forward reaction rate R1 and the backward reaction rate R2 are equal. But if we remove the products C plus D from the mixture, then the rate R2 will become less than the rate R1, which means there will be more product formation. This is what is used to increase the yield. Please notice here that R1 is not changed. Instead, R2 is reduced. R1 remains the same while R2 is reduced. That is how we increase the yield. Therefore, the statement B is false. The statement C is about this rate limiting step. The rate limiting step in a series of reactions consisting of elementary reactions is determined by the slowest elementary reaction. If it is hard for you to understand that, imagine a production line. if they are producing a mask and someone is keeping the two materials together and someone is stitching the materials together and then someone is putting the strings for the ears, then one after the other, then if one person is very slow at their job, that means the overall rate of the production of the masks will be determined by that slow person. That is how the elementary reaction also determines the rate of a series of elementary reactions. Statement D is about the spontaneity of reaction, which is usually expressed in Gibbs energy. The spontaneity is determined by the entropy of a reaction, the temperature at which it is occurring, and also the enthalpy value of the reaction. These three factors determine only the spontaneity of a reaction. They do not determine the rate of reaction. They have no connection to that. The structure of the compound in question 35 is given. Of the two carbons involved in the double bond, this carbon has two different groups attached to it, but the other carbon has the same two groups attached to it. Therefore, there is no geometric isomerism. Reacting with HBr, hydrogen is added to the carbon atom which already has more hydrogen, and bromine is added to the other carbon atom. This produces a chiral carbon with four different groups. Therefore, there is optical isomerism. Reacting with CH3MgBr, the CH3 molecule attacks the carbonyl carbon to form the end product shown here. Here also there is a chiral carbon with four different groups attached to it. Therefore, there is optical isomerism. Pure nitric acid is colorless, but its spontaneous decomposition produces nitrogen dioxide, which is brown colored. Therefore, nitric acid solutions in the laboratory are brownish. To find the patterns in the bond lengths between nitrogen and oxygen in nitric acid, we have to consider the resonance structures of this molecule. Of the three resonance structures that has been drawn here, it is the first two resonance structures which are more stable because of the presence of the negative charge in the more electronegative atom of oxygen. Therefore, it is these two structures that are most important in producing the final resonant structure of nitric acid. Considering that, we can say that these two bonds will be equal in length, but the third bond would not be equal in length to the other two. Nitric acid cannot act as a reducing agent because the nitrogen atom, which is the central atom of the acid, is already in its maximum oxidation state and therefore cannot give out further electrons. Among the uses of nitric acid is the production of fertilizers, including ammonium nitrate. In question number 37, we are given a calculation. It says that Cs and oxygen gas together to form CO2 of 0.4 moles amount releases an amount of energy equal to 40 kilojoules. So the molar enthalpy would be the amount of energy released per mole, which would be 100 kilojoule per mole. In statement B, it is mentioned that heat is required, but the question states that heat is released as in most combustion reactions. Therefore, we cannot say that energy is required, so it is false. But the value 24 kilojoules is the value that is released when 11 grams, that is 1/4 of a mole of CO2 is formed. In statement C and D, we are supposed to use the relationship between the enthalpy of formation of products and reactants in order to find the enthalpy of the reaction. So here energy is released, that means the reaction has a negative enthalpy, that means the delta H formation of reactants is higher than that of the products. The key word in question number 38 is that this is an elementary reaction. Therefore, there are no steps within the reaction. The rate depends on how often the reactants themselves will collide. This is a factor of probability and therefore is proportional to the concentration of reactants. If there are two molecules A and B involved in the reactant side, then the rate of reaction is going to be directly proportional to both A and B. If in another reaction B itself is actually A, then again the rate of reaction is going to be proportional to both concentrations. Therefore, in such a situation, a stoichiometric number will be used as the order. This should make it clear that the order of reaction is the molecularity. It cannot be less than the molecularity because this is an elementary reaction. Neither can it be higher for the same reason. And the molecularity cannot be zero as well because in an elementary reaction, all the reactants play an equally important role in determining the rate of reaction. The double bond carbons in this compound is brominated by adding bromine aqueous, which is brown. Once this reaction occurs, the bromine aqueous solution concentration reduces and therefore it will become colorless. Reaction of an amide with a hydroxide ion, as in sodium hydroxide, will produce a carboxylate ion liberating ammonia. 2,4-DNP, which is known as Brady's reagent, reacts with aldehydes and ketones to produce a precipitate, but not with amides. Sodium borohydride is capable of reducing aldehydes and ketones, but they are not capable of producing acetic acid and amides. On the other hand, lithium aluminum hydride has the capacity to turn amides into amines. The two thermosetting polymers studied are urea formaldehyde and bakelite. Urea formaldehyde has urea and formaldehyde as components, and bakelite has phenol and formaldehyde as components. Therefore, the choices A and B are correct. Concentrated H2SO4 is a powerful dehydrating agent. If it is poured carefully onto a pile of sugar crystals, which is consisting of sucrose, then hydrogen and oxygen are removed from the sugar as water, and a sticky black deposit of carbon is left, which actually erupts, growing because of carbon monoxide and carbon dioxide also being produced as part of the reaction. Here notice that the oxidation state of carbon is not going to the maximum of +4, rather it remains the same. Therefore, the action here is not oxidation but dehydration. Overall reaction of hydrohalogenation of alkanes is given in this. Here notice that there is an intermediate formed when one of the bonds involved in the double bond attracts a proton, that is an H+ ion, and therefore there is a positive charge in the carbon atom involved in this. And this positive charge must be stabilized. And there are two ways in which this reaction can occur. Either the carbon on this end or the carbon on this end can obtain this positive charge. But the stability is higher if there are more alkyl groups attached to the carbon involved, because alkyl groups can repel electrons towards the positive charge containing carbon. And therefore, the formation of secondary or tertiary carbocations are favored rather than the formation of primary carbocations, which is what is given in the question. Therefore, statement 1 is false, while the second statement is true. The average molecular speed of hydrogen and nitrogen are compared in the statement in the first column of question 43. The average molecular speed is proportional to the absolute temperature's square root and inversely proportional to the square root of the molar mass. Therefore, hydrogen at any temperature will have a higher velocity, molecular speed, than nitrogen because it has a lower molecular mass. In addition, in this question, nitrogen is also at a lower temperature. Therefore, obviously, hydrogen is going to have a higher molecular speed. In the second statement, there is a key word that is missing. The average molecular speed is directly proportional to the square root of the absolute temperature, not just temperature. Therefore, that statement is also considered as false. As the radius of the alkali metals increase as we go down the group, the ionization energy decreases, and therefore the formation of cations is easier, and therefore they become more reactive. For example, while lithium does not react vigorously with water, sodium reacts vigorously while moving, and it will only burn if you try to retain the sodium in one place. On the other hand, potassium will immediately burn if you put it in water, and rubidium should never be put in water because of the highly exothermic nature of the reaction. The terminal hydrogens attached to the sp hybridized carbon atoms in alkynes have acidic properties, and therefore they can be replaced by metals like sodium, copper, and Ag. Therefore, both the statements can be taken as true. Silver acetylide is grayish or white. Copper acetylide is reddish. Question number 46 is based on the idea of Gibbs free energy, which determines the spontaneity of a reaction. If Gibbs free energy is 0 or negative, then the reaction is spontaneous. If it is positive, then it is non-spontaneous. The spontaneity of a reaction is determined by the energy released and the entropy achieved. Entropy is disorder. So if a reaction releases energy, then it is more likely to be spontaneous, but not always. If a reaction increases disorder, that is entropy, then it is more likely to be spontaneous, but not always, because it depends on both enthalpy and entropy. As an example, look at the phase change of ice into water. This is an endothermic reaction, that is, it requires heat, but in the room temperature, it constantly keeps happening. Similarly is the reaction of dissolution of ammonium nitrate. This is also endothermic. And in the second statement, we see that the relationship for Gibbs free energy is given incorrectly, considering that entropy has a positive. And in relation to the question, we can also analyze which are the reactions that are always spontaneous, which are the ones that are always non-spontaneous, and which are the ones we cannot predict. If a reaction both increases entropy and releases energy, then it is always spontaneous. If a reaction absorbs energy and decreases entropy, then it is never spontaneous. And the other two conditions, we cannot make a prediction. It depends on the interplay of both entropy and enthalpy. Production of ammonia through the Haber process using nitrogen and hydrogen is an exothermic reaction. But this reaction occurs at a high temperature of 450 degrees Celsius. This is to increase the rate of reaction. The forward reaction is favored because the products are constantly removed from the system. Among the uses of ammonia are the production of nitric acid and fertilizers such as urea. It is true that enantiomers are isomers which are non-superimposable mirror images of each other. For a compound to be non-superimposable with its mirror image, it must contain a chiral atom, that is, it must be attached to 4 different groups. Example, here X is attached to A, B, and C and D. If at least 2 of these groups are same as in the example given in the question, then the 2 mirror images become superimposable. The solubility of barium oxalate in acidic medium is higher because C2O42- will be removed through the reaction given here when acid is added, and therefore the dissolution reaction of barium oxalate will be driven forward and therefore solubility will increase. The bond energy of the N2 molecule, because of the triple bond in between them, is very high and therefore it is very unreactive. It is true that nitrogen is fixed at the root nodules of certain plants because of the presence of certain bacteria, and its action is through their enzymes.